A binomial experiment is an experiment where there are exactly two possible outcomes for each trial of interest called success and failure. This means that even if there are not normally two outcomes for this type of experiment, in this case, we can identify one as success and the others as failure. For a binomial experiment, there's always a fixed number of trials, n trials. The n trials are independent and they're repeated under identical conditions. Each trial has only two outcomes that can be identified as success and failure. Again, this means that we've identified some outcome as success and then every other outcome as failure. For each trial, we call the probability of success P, and it's the same for each trial. We call the probability of failure Q. So, since each trial results in either success or failure, we can say that P plus Q equals 1, which means that Q is equal to 1 minus P. So, for instance, if we determine that P is equal to 60% or 0.6, then Q is equal to 1 minus 60% or 0.4. Finally, our object is to find the probability of R successes out of n trials. Let's look at some experiments that are binomial experiments. Tossing a coin 20 times to see how many heads occur. In this case, the fixed number of trials is 20. Success is flipping heads. And failure is not flipping heads, or in this case, flipping tails. The probability of success in this case is 1/2, or 0.5. And then the probability of failure is 1 minus 0.5, or 0.5 as well. Asking 200 people if they are under 25 years old is a binomial experiment. N is fixed at 200 trials. Success is under 25 years old. And failure is person is not under 25 years old. Or that they're 25 or older. We can't determine the probability of success or failure in here because we weren't given that information. Rolling a die 100 times to see how many times a 5 appears. In this case, n is 100. Success is rolling a 5. And failure is not rolling a 5. When a die is rolled, there are 6 outcomes. However, in this case, we are determining rolling a 5 to be success and rolling anything else to be failure. So not rolling a 5 means we rolled a 1, 2, 3, 4, or 6. In this case, we can determine the probability of success and failure. The probability of success is 1/6, and the probability of failure is 1 minus 1/6, or 5/6. Let's look at a few examples that are not binomial experiments. For example, asking 200 people how old they are. In this case, we do have a fixed number of trials. But we do not have anything that we can determine success or failure. So while n is 200, we don't have anything we can call success because the outcomes of this will be things like people's ages rather than being able to determine if something's less than 25 or not. In this case, rolling a die until 5 appears is not a binomial experiment. We do have success by calling success a 5, but we do not have a fixed number of trials. And drawing 5 cards from a deck for a poker hand is not a binomial experiment because while we do have a fixed number of trials, we don't have anything that's success or failure, and the trials are not independent. Once we pull a card out of the deck, the probability of obtaining any of the other cards in the deck changes. To compute the binomial probabilities, we will use the following formula. The probability of our successes, so however many successes we are looking to get in our certain number of trials, is the combination for n trials and r successes times p, which recall is the probability of success, raised to the r. R is the number of successes. Q is the probability of failure. Where n minus r ends up being the number of failures. For example, a coin is flipped 5 times. What is the probability of getting exactly 2 heads? In this case, n is 5. Success is flipping heads. Failure is flipping tails. Probability of success is 0.5. Probability of failure is also 0.5. And we are looking for the probability that r is equal to 2 because we're looking for the probability that we get exactly 2 heads, so 2 successes. So we have C, n is 5, r is 2, times P, which is 0.5, raised to the number of successes we're looking for, which is 2, times the probability of failure, 0.5, raised to the number of failures. If we are flipping a coin 5 times and we are getting 2 successes, then we get 5 minus 2 failures, or 3 failures. This can be substituted directly into a scientific or graphing calculator. For this piece, you may use the button for combinations, which normally says NCR, or sometimes does say C parentheses NR. This can all be done in one step, and we get 0.3125 for the probability. This comes out to be exact, so there's no reason to round it. For the same question, let's calculate the probability that we get at least 2 heads. In this case, we're saying we want R to be at least 2. So 2, 3, 4, or 5. We know it stops at 5 because we're only flipping the coin 5 times. To actually calculate this, we would say the probability that R is greater than or equal to 2. We can say this and don't have to write this because we know n stops at 5. In this case, this technically equals the probability that R equals 2, plus the probability that R equals 3, plus the probability that R equals 4, plus the probability that R equals 5. We did already calculate the probability that R equals 2 in the previous part, but then we would still have to calculate 3 more probabilities. What may be shorter is to say we can use the complement and calculate the 1 minus the probability that R equals 0, plus the probability that r equals 1. Since n is 5, it means we have the following possible outcomes for r. 0, 1, 2, 3, 4, 5. We're looking for this piece. We would have to add up all of those probabilities. In this case, it seems a little shorter, even though we already calculated the probability that r equals 2, to calculate the other two probabilities and use the property of complements to subtract it from 1 and find the probability. So, for the probability that r equals 0, which we will do both of these separately, we have 5, 0 times p, which is still 0.5. Now for this piece, we're looking for 0 successes times the probability of failure raised to the number of failures. If we have 0 successes, that means we have 5 failures. Now let's write the probability that r equals 1. So we have the same expression, however, now we have 1, 0.5 to the first for 1 success, times 0.5 to the fourth. And again, we will calculate these separately. For the first part, we get that the probability that r equals 0 is 0.03125. For the probability that r equals 1, we get 0.15625. Adding these two together gives us 1 minus 0.1875, and then doing the final subtraction, we get 0.8125. And this is the probability of getting at least 2 heads when we flip a coin 5 times. In this example, a biologist is studying a new hybrid tomato. It is known that the seeds of this hybrid tomato have a probability of 0.7 of germinating. The biologist plants 6 seeds. So, n is equal to 6. Success is that a seed germinates. We are told in this problem that p, the probability of success, is 0.7. Failure in this case is that a seed does not germinate. And in this case, probability of failure is 1 minus 0.70, or 0.3. In part A, we are looking for the probability that exactly 4 seeds germinate, or the probability that r is 4. So we have n is 6, r is 4, times 0.7 to the number of successes we're looking for, which is 4, times 0.3 to the number of failures in this case. If we have 4 successes, we have 6 minus 4, or 2 failures. Again, these probabilities can be calculated all at once on a graphing or a scientific calculator. We get 0.324135. We can leave this like this, or we may round it, depending on the problem. For the probability that at least 4 seeds will germinate, we are looking for the probability that r is greater than or equal to 4. Again, at least 4 means 4 or greater. In this case, since n is 6, we know that r is greater than or equal to 4, means that we're looking for the probability that r is 4, 5, or 6. Again, all possibilities for r in this, for the number of successes, are 0, 1, 2, 3, 4, 5, and 6. We're only looking for this piece, and we have already calculated the probability that r is 4, so in this case, it's not quicker to use the complement. We will just calculate the probability that r equals 4 plus the probability that r equals 5 plus the probability that r equals 6. We've already calculated the probability that r equals 4, so we can use that from the previous part. The probability that r equals 5 is C 6, 5 times 0.7 to the number of successes, which is 5, times 0.3 to the number of failures, which would be 6 minus 5, or 1, plus the probability that r equals 6, which is C 6, 6 times 0.7 to the number of successes, in this case is 6, times 0.3 to the number of failures, which is 0. Again, this can be calculated all at one time for each individual probability. So the probability that r equals 5 comes out to be 0.302526. The probability that r equals 6 comes out to be 0.117649. If we add these all together, we get 0.74431, and this is the probability that at least 4 seeds will germinate. In this example, we're looking at a 10-question multiple choice quiz where there are 4 choices for each question. In this case, the student is guessing on all of the questions, so we will assume that the student has a 0.25 probability of guessing the question correctly. So, since there are 10 questions, this makes n 10. Success is that he answers the question correctly. The probability of success is 0.25, since there are 4 choices. Failure is that he answers incorrectly. Probability of failure is 1 minus 0.25, or 0.75. To say he will answer all questions incorrectly means in this case we're looking for the probability that r equals 10. So we have C 10 for n and 10 for r. Probability of success is 0.25 raised to the 10th times the probability of failure, 0.75 raised to the 0. In this case, the number that comes up looks something like this. Remember that if your calculator displays something like this, it's giving it to you in scientific notation. So this means 9.536743164 times 10 to the negative 7. This tells us to move the decimal point over 7 places, which will give us 0.000000954 approximately. So this is very close to 0. In most cases, you would be able to round this probability to be about 0, which makes sense because it's very unlikely that he would guess all 10 questions correct. If we're looking for the probability that he will answer all of the questions incorrectly, this means we're looking for the probability that r is equal to 0, or no successes. In this case, we have C 10, 0 times the probability of success, which is 0.25. Since he's answering all questions incorrectly, this is to the 0, times 0.75 to the 10th. So the probability that he would get all of the questions wrong is about 0.0563. Since this is a rounded answer, because the decimal is extremely long, we will put that it is approximate. To calculate the probability that he will answer at least one of the questions incorrectly means that we're looking for the probability that R is 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. So if we were to calculate this just like this, we would be looking for the probability that R is greater than or equal to 1, which means we would have to calculate each one of these probabilities and add these all up. However, we know that the only value of R we're missing here is 0. That would be quicker no matter what, but we've already calculated the probability that R is 0 from the previous part. We got that to be about 0.0563. All we have to do is subtract this from 1, and we have our answer.